We need to see if the machine needs to be adjusted, so we would like to do probably a hypothesis test. And we are going to need, it says we're looking, the parameter that we're interested in, okay, so we want to answer the question, should the machine be adjusted? When would we adjust the machine? If it's, well, what if it's less than 12 ounces? If it's different than 12 ounces, so you can have more than 12 or less than 12. Who's going to, when are customers going to complain more? When there's less than 12 ounces, okay? So you have, but you have to look at both. If you overfill the can, couldn't the cans explode? And then you'll still have mad customers. So this is different than, this is going to be a not equal to alternative hypothesis. And are we going to be dealing with mu, or are we going to be dealing with p? Mu and x bar or p and p hat? Is it a proportion? Is it a mean? It's a mean. So we need to, from this data, we need to figure out what is the mean, what is the sample mean, what is the true mean that we desire, and then we'll also need the standard deviation, and we'll want n, and we'll also want our degrees of freedom. So this is all stuff that we want to gather up before we start doing our hypothesis test. So what is the true mean that we desire our cans to be filled with? 12 ounces. Okay, so how are we going to calculate the sample mean? Why don't we put them in a list? Because then we can do one variable stats, and we will be able to do the mean and the standard deviation. And then later when we check conditions, we'll have to do a normal probability plot. So go to stat, I want to edit my lists, and I'm just going to enter 12. You should all be doing this right now, putting your data in your list. Alright, so now I have all my data in the list. I'm going to do stat, calc, one variable stats from whatever your list is. So I got that my sample mean is 12.016 repeating. And the sample standard deviation is the S1. Okay, S is the one you use, 0.0391. Actually, the more decimals you carry out, the more accurate you're going to have for your hypothesis test. So N is 9, and what would be my degrees of freedom then? 8. All right, so does it appear that the machine is filled, that they're being filled different than 12 ounces? Okay, all right. I mean, you might say not much, but can that make a difference if your can only supports like 12.02 ounces? I mean, if you think of a machine filling things up, do you think if it gets a little bit above, it has maybe a tendency to keep getting more and more over time, like the machine keeps getting off little by little, so pretty soon it's going to be filling it to 12.02 and 12.025, and so you know, your cans are going to explode then too soon. All right, so it does appear that it's maybe different from 12, just because it's not exactly 12, right? So you can do step 1 or step 2 first. I mean, at first glance, okay, what does it appear? At first glance, it appears that the can's volume is not 12 ounces. We don't need to say greater than or less than because it's not asking us for that scenario. It's just saying different from. So at first glance, it appears that the can's volume is. You're filling the can. You're not making a can. You're filling it with soda. The can's volume is not 12 ounces. Since X bar is equal to 12.016 repeating. Why? What could this be because of? Okay, so this difference could be due to sampling variability. So I will conduct, now what type of hypothesis test are we doing? How many samples have we taken? One sample. Everything we've done so far is one sample, so that should be easy. A one sample, what type of test? T or Z? T test for what variable? For mu. You could say for the mean. That's fine. You have to name your test like that. Okay, so I will conduct a one sample T test for mu at what alpha level would you like to do?
0.05.
You want to do 0.05? Well, I mean, you don't always have to. I mean, I think 10% is probably a little, I mean, I don't know, a little high here. I think 0.05 is good.
It's so hard to decide.
Then just pick 0.05. Okay, so we're going to do a one sample T-test for a mean. And so our hypotheses, the null hypothesis is that the true mean is what? 12 ounces. And the alternative hypothesis is that the mean is not equal to 12 ounces. This is a two-sided or two-tailed test. Okay, it's two-sided or two-tailed. So when we go to draw our normal curve, once we find our t-value, t and t, we're going to have to go below and above. Now, we'll take care of that when we start doing the calculation. So what is the next step? What do we... Okay, check our conditions. So conditions and assumptions. Okay, so stated as a random sample of 9 cans, stated as a random sample of 9 cans volumes. Okay, and second, can we assume that 9 is less than 10% of all cans produced in an hour? Okay, assume 9 cans is less than 10% of all cans in 1 hour, because they do this every single hour. All right, and the third condition, is this a large sample size? N is not greater than 30, N is equal to 9. So what do we have to check? So check NPP, normal probability plot. So I get my calculator out, and I go to second stat plot. I go to my stat, I make sure it's on. I go to the last type, tell them where my data is, and I hit graph, and then I zoom 9. And then I must replicate that drawing somewhat on my paper. So this is the normal probability plot. Does that look roughly linear? Roughly linear. It does. It looks roughly linear. I'm not going to proceed with caution. You don't need to spend even 2 minutes debating, okay? Yes, it kind of looks like it's a little curve, but if I draw that line there, you know. So since the NPP is roughly linear, we can assume what? What can we assume? Okay, we can assume approximately normal. Or you could just say normality is another way to say that. Yeah, the normal probability plot is what you say. Since the normal probability plot is roughly linear, we can assume normality. All right, so all the conditions and assumptions are met, so we can do our calculations. And we need to do our probability. So the probability we start out with is that our sample mean is not equal to 12.016 repeating. And it might be easiest at this point, you know, it might be easiest for this problem, instead of having to type a bunch of 6s, we could call it 12.017, because it would round to 7, wouldn't it? Because the next, if it's 6 repeating, okay. So that's what we're going to use instead, just so we can end it in our calculator. Now, we don't have, if we're going to show our calculations, then we don't have a not equal to. So that is 2 times the probability that x is. Now, we want to make the correct statement here. And this is where, are you all listening? I could say less than, I could say greater than, but it has to make sense with our data in comparison to the true mean. So our data was 12.017. Is that greater than or less than the true mean that we desire? It is greater than. So we are going to do the greater than side. Okay, when you do a two-sided test, that's when you decide which it is. It has to be your data. How does it compare to the true mean? So this is what we're going to find now we're going to find the t-value that goes with this. So now the last thing you are going to do is take the probability times 2. So this will be the probability that t is greater than 12.017 minus 12, the observed mean minus the hypothesized mean over the standard deviation 0.391 divided by the square root of 9. So when you do that in your calculator, your t-score becomes, your t-value, 1.304. Now I'm going to do 2 times TCDF. Okay, so if we're doing the greater than, we're doing this up here, 1.304. This is the side we're doing. It's the same as this. It'll be the same probability as this side. That's why we multiply by 2 in the end. Okay, so TCDF, if this is what I'm doing, what's my lower bound? 1.304. What's my upper bound? Infinity. And what's my degrees of freedom? 8 degrees of freedom. Lower bound, upper bound, degrees of freedom. So get your calculators out. Second distribution, TCDF, 1.304, and then 99999, and then 8 degrees of freedom. And I get that my p-value is going to be 2 times 0.114. And take that times 2, and I get my p-value. This is my p-value now. My p-value is 0.2285. Compare that to alpha. What's alpha? 0.05. 0.05. Greater than or less than? Greater than. So what do I do?
Fail to reject.
Okay, I fail to reject the null. Now, if you just stop it with that, you're not going to get any credit. You have to put it in the context of the problem. Fail to reject the null. So what are you deciding? If you fail to reject this null, what have you decided?
That the true mean
Let's do it real, like the machine doesn't need to be adjusted. Okay, I fail to reject the null. The machine does not need to be adjusted. Okay, now maybe the next hour it'll be more off and you will need to adjust it. But as of right now, we do not need to adjust the machine. Okay, so I want to show you something kind of cool here, and Tommy mentioned it earlier. You still have to show the formula and stuff, but your calculator can actually do this test for you. So as long as you can do it either if you've got the data, you still have to enter the data in the list. So if you go to Stat and then go over to Tests, so you're going to go to Stat and then you're going to go over to Tests. It really does have all kinds of tests. It has a z-test, a t-test, a 2-sample, a 1 proportion, so that's for your proportion. We're just going to do a t-test here. So when you highlight t-test, so you're going to do a t-test. And then, do you have the data? Okay, we have the data. So we highlight the data, it's in. And then what is the, let's see, we have the data. And now this is the null hypothesis. So what is the mean of the null hypothesis? 12. So that's the mean of the null hypothesis.